We present a new general representation for proximal interactions that exploits dynamic motions for understanding objects and scenes. We track interactions and efficiently encode them to obtain a new functional descriptor for the object, its interaction landscape. We observe an active object, the so-called motion driver, performing an interaction on a passive object, the motion receiver. To capture an interaction, we distribute particles on the surface of the motion driver. We track motions by placing sensors in the interaction space of the motion receiver. Each sensor defines a cuboidal region that allows us to track bypassing motion particles. Tracking particles in these sensor regions allows us to capture their motion trajectories. Each trajectory encodes the positional changes of a particle and its velocity over time. The set of trajectories represents the interaction that we can now analyze. We encode the motion flow of an interaction by converting each sensor region to a 3D vector field. We analyze the captured motion by computing a set of its first-order attributes, such as vorticity, dilation, and shear strain rate. We use the vector field attributes to quantify the measured interaction by computing a set of histograms. For example, the interaction of grasping a cup might have more vorticity than sitting down on a chair. The histograms allow us to describe these differences. To facilitate the comparison of two interactions represented by two sets of vector fields and their corresponding histograms, we compute a global histogram for each attribute and over all vector fields. We define our interaction descriptor as a set of these global histograms encoding the motion patterns of a motion driver performing an interaction on a motion receiver. To compare two interactions, we compute the relative distance between two sets of these histograms. Our descriptor can be used to encode interactions from various sources, including character animations, simulations for grasping in fluids, as well as real-world data such as motion capture and RGBD scans. Unlike previous approaches, we are not limited to static scenes and rigid surfaces, but instead provide a more general means to explore interactions. We show how to factorize interactions and how to use them for common shape retrieval and classification tasks. Additionally, we perform a number of evaluations against state-of-the-art descriptors for static scenes. Unlike previous approaches, we are not limited to static scenes and rigid surfaces, but instead exploit dynamic properties in the interactions. Embedding a shape in its interaction space enables a more thorough understanding of its functionality, a key requirement in many application areas. Employed for shape retrieval, our descriptor allows to retrieve objects that share the same functionality, even if their geometry differs. We demonstrate the effectiveness of our interaction descriptor by employing it for salience estimation and shape correspondence tasks, which both greatly benefit from knowing about the functionality of the shape. Thank you.